In this series of lectures, we'll start looking at spectral representation of signals, and in particular, we'll look at the Fourier series. So, in many experiments, one encounters signals that can be thought of as a combination of individual signals with different frequencies. For example, consider, let's say, we have some signal defined by the function f of t, and let's say that in some experiment we measure this kind of signal. Now this signal can be composed of, or it might consist of, many individual signals. For example, there might be this wave, and or we can say that this signal might be a combination of this signal and some other signal with higher frequency. The point is that we have a signal which might be which can be thought of as a combination of signals with different frequencies. So such kind of signals, it is useful to represent these signals in as sum of sines and cosines, or what we say as sum of harmonic functions, which include sine and cosine functions with different frequencies. So that means we can represent and analyze signal which is in time domain. So this signal depends upon time, and that signal, instead of looking at that signal as a function of time, we may look at that signal as a function of frequency. So that's an alternative representation of the signal, and that is what we call as the spectral representation of the signal. So such a representation of signals in terms of frequencies that constitute the spectrum has several benefits. Okay, so one benefit is that, let's say that we have a signal in time domain which may be combination of many other signals, and we want to know what is the strength of the component with a particular frequency compared with the strength of the component, the signal component with another frequency. Then we would like to also design filters so that maybe I want to remove a signal with higher frequency while retaining the signal with lower frequency. And many times what we have is that we have a signal where the true signal is hidden underneath experimental noise. So we might have a signal which might look very noisy, and that's because there's some noise overriding the signal. So we want to get rid of this noise and find the true signal. So it helps in such cases that we look at the signal in terms of the frequency rather than as a function of time. Okay, so let's so that's why we are interested in the spectral representation of signals. So what we'll do is that we'll begin with a particular type of functions called the periodic functions. So let's consider functions which which have this property that, let's say I have a signal defined by a function f of t, and if this function repeats itself after a time period capital T, so in that case I can say that f of t is equal to f of t plus n times capital T, where n can be some integer value or any integer value. So here t is called the the time period, and note that t is the smallest number for which this property holds, and hence this time period t is called the fundamental time period. So periodic functions will repeat themselves after time period t. So for example, let's say that this function is periodic, and here this is the time period t. So after this in time interval, this function repeats itself. Now, in all our discussions, we'll look at signals which are functions of time. Okay, but we can also have signals that are periodic in space. So just because we have to choose some variable to do our analysis, so let's go ahead with the independent variable time, although the same analysis also applies for space. And many times, the any physical phenomena will exhibit periodicity which is in both space and time. For example, we have wave phenomena. So you might have a wave, let's say, in space defined by this function, and then at a later time this wave moves ahead. So even in space this has a wave like nature, and whereas if you note the amplitude of this wave at a particular time, even then you will have this periodic nature. So but for our analysis, let's stick to one independent variable, which is the time. So a periodic signal, let's say we call it f of t, can be represented in general as an infinite sum of harmonic functions. So if we have this periodic function f of t, I can represent it as a sum of this constant value a naught by 2 and sum of sines and cosines. So I may have an cosine 2 pi n t over capital T, which is the time period after which the function repeats itself, plus bn, which is a constant, times 2 pi n t over t. So this kind of representation of a function in terms of sums of sines and cosines is called Fourier series. So alternatively, I can also represent the Fourier series as this. as cosine n omega 1t plus bn times sine n omega 1t, where omega 1 is the fundamental frequency, and that is given by 2 pi over capital T. So this spectral representation of a signal is called the Fourier series. Now what we want to do is that we need to determine the coefficients of this series. So the coefficients of this Fourier series can be obtained by noting that cosine and sine functions are orthogonal with respect to each other. So what this means is that if I take, let's say, sine of 2 pi n t over capital T times sine of 2 pi m t over capital T, and I take product of these two sine functions and integrate them over one time period. So let's say minus t by 2 to t by 2, then the value of this integral is t by 2 when n is equal to m, and for all other cases this value is identically equal to 0 when n is not equal to m. So the point is that if I multiply two such sine functions but with different frequencies, then if I integrate over one whole time period, then the integral is 0. Otherwise, if I multiply the same function, and in that case I will have sine. So if n is equal to m, then this part would be sine squared 2 pi n t over t, and that I can write as, and then if I integrate this over minus t by 2 to t by 2, then I will get this value t by 2. Otherwise, if we have n which is not equal to m, then I can write this product as sum of two cosines, and then when I integrate those two functions and those two cosines, I'll get again two sine terms, which if I put the limits, you will see that you'll get 0. So only if we multiply two such functions with same value of n and m, then we get a non-zero integral. Otherwise we'll get the zero integral. Similarly, if I perform this integration from minus t by 2 to t by 2, where capital T denotes the time period, then if I take product of two cosines with different frequencies, then again it is easy to show that this integral is equal to t by 2 when n is equal to m, and note that this is the case when n is not equal to 0. Okay, When n is 0, then we'll have the constant term that we'll handle independently. And then when n is not equal to m, then this integral is 0. Similarly, if I look at product of cosine 2 pi n t over t and sine 2 pi m t over capital T, then this integral is always equal to 0. And obviously, if I take any of these sine terms, let's say sine or cosine terms, and perform an integration over one whole time period, then this is 0. And similarly for cosine also. So this is what we mean by the orthogonality of sines and cosines. Now, using this orthogonality property, we can find the coefficients of our Fourier series. So these are the coefficients that we want to find. So these coefficients are a naught and an and bn, where n goes from 1 to infinity. So in general, you will have infinite number of these coefficients. In particular, we'll have countably infinite number of these coefficients, which we need to determine to represent a signal in time domain in terms of these in terms of the frequencies. So now let's start looking at how we can find these coefficients. So let's again start by representing this periodic function f of t in terms of the Fourier series. Okay, so the first step is that let's try to find this coefficient a naught. So we know that if we integrate these cosine and sine functions over one whole time period, then these integrals are 0. So what we'll do is that we'll integrate both sides over the time interval minus t by 2 to t by 2, and we note that if we perform this integral for all these terms, then that integral would be 0, as we have seen earlier. So we are just left with one term on the right hand side, which is equal to t. So this means that a naught can be a naught is given by 2 over the time period t and integral over the interval minus t by 2 to capital T by 2 f of t dt. So this is my coefficient a naught. Now to find these coefficients an and bn, we now use the orthogonality property of the sines and cosines. So let's say that, okay, so if we want to find the coefficient an, so what we will do is that we'll multiply both sides of this equation with cosine 2 pi n t over t, and here also cosine 2 pi n t over t and integrate. So when I do this integration, we'll see that only that integral remains where I have product of two cosine functions with same frequency, that is for the same value of n. Therefore, what we'll get is that, so from the left hand side, we'll get an integral minus t by 2 to t by 2 f of t times cosine 2 pi n t over the time period capital T dt, and on the right hand side we'll just have one integral because all other integrals which have cross terms, for example product of sines and cosines or cosines with other cosines but with different frequencies, those will be zero. So we'll just be left with one integral on the right hand side, and that integral is this. And we know that this integral, I can either directly use the result that I had presented above. So this integral over here is equal to t by 2. So I can write, so this whole integral is t by 2, so this whole thing on the right hand side is an times t by 2. Therefore, I can write an as, if you can see over here, so I have this term multiplied by 2 over t. So that means an is given by 2 over t f of t times cosine 2 pi n t over t times dt. So with a similar method, we can find that the coefficients bn, which correspond to the sine terms, are given by 2 over t minus t by 2 by 2. So we take our original signal or the periodic function over one time period, we multiply it with the particular sine function with frequency, that is n times the frequency, the fundamental frequency. So this whole thing over here, that is the argument of the sine function, is also actually n times omega 1 times t, where omega 1 is my fundamental frequency. So now we have found all the coefficients of the Fourier series. I have a0, I have bn, and I have an. So if I know these coefficients, I can write any function, any periodic function, as sum of sines and uh, cosines, where the coefficients a0, an, and bn are given by these three integrals. So one point to note is that if we try to represent a function which is in time domain in terms of the Fourier series, then the advantage is that, let's say I have a function that is periodic with time period capital T, but you see that this function is defined for infinite number of points in time. Now the same function, if I try to represent in terms of the different frequencies, then I have again infinite number of coefficients a naught, an, bn, where n goes from 1 to infinity. But what we see is that these rather than having infinite number function defined at infinite number of times, now even though I have infinite number of frequencies, these are some countably infinite number of frequencies, discrete frequencies. So sometimes we'll see, as we'll see later, that instead of representing this function in time domain, if we represent this function in terms of the frequencies, which will be n times omega 1, then all we need is to represent this function is to just give the coefficients, let's say value of coefficients at these discrete frequencies. So these are the coefficients an, and we can include a value of a naught also, and similarly we'll have coefficients bn corresponding to the sine terms. So the point is that a function that is continuous in time domain, I can represent that using Fourier series in terms of some discrete frequencies.